Welcome to my new series on categories of modules. In the series, we're going to be motivated by the following consideration. If two rings are isomorphic, then, well, hopefully you at least believe, but we're going to prove this in due time, that their module categories should be equivalent. In fact, if the rings are isomorphic, the module category should even be isomorphic, a stronger concept. But famously, the converse does not hold in general. For example, the category of Q vector spaces, so Q modules, Q vector spaces, is equivalent to the category of modules over the algebra of 2 by 2 matrices, valued in the rational numbers. However, one of these rings is commutative, one of these rings isn't, and so clearly the converse doesn't hold. So what can we say about equivalent categories of modules? Now, a more traditional course in rings and modules might first study rings and intrinsic properties to rings, certain kinds of ideals and ideal theoretic properties, and then later translate that into categorical statements. That is not the approach that we're taking. Another common approach to a categories of modules course would be something that would say do some homological algebra and talk about the classification of modules over a PID. This is also not the approach that we're going to be taking. Instead, we're sort of going to work towards understanding equivalences of categories between rings. So this is called the Merida equivalence, by the way. If two rings, if their module categories are equivalent, we say that the rings are Merida equivalent. And I would personally really like to also move towards an understanding of the auto-equivalences of the category of R modules. And so if one collapses the auto-equivalences up to isomorphism of functors, secretly this is a two group, don't worry about what that is now, we'll get to it. But if we collapse those things, we get some sort of honest group. And in the case that R is commutative, there are some nice papers that I hope, if I forget, you'll yell at me in the comments to include in the video description, that this group will actually be isomorphic to a semi-direct product of the automorphisms of the ring and the Picard group of the ring. So there's sort of a nice interpretation in the commutative case. So a question that I'm wondering, and this video series is an excuse for me to build up more of the tools to explore, is what are more general cases in which we can have a nice description of this. So the general context by which one normally approaches these questions are the Merida theorems. So there's sort of three important theorems due to Merida that classify, to a certain extent, equivalences of categories of R modules. And so we're going to be building up towards those theorems. But before we get there, I would also like to touch upon, so coming back to this question about when we have, one direction we know, the converse direction we don't in general. However, if we assume ahead of time that both rings, so this would not be an example, if we assume ahead of time that both R and S are commutative, then it turns out that the rings are isomorphic if and only if the module categories are equivalent. And the way that we're going to do this, the way that we're going to build this up is through an extra layer of abstraction. But I want you to keep in mind our motivation is ultimately to prove this result about commutative rings. So in particular, the direction we'd like to head towards is if R and S are commutative and their module categories are equivalent, then R and S are isomorphic. The way that we do this is that there's a concept known as the center of a category, which we will define in today's episode. And it turns out that for the category of modules, this has a ring structure, and that is isomorphic to the center of the ring in any case, whether R is commutative or not. And so, of course, in the commutative case, one gets that R is isomorphic to its center. And so one can imagine the center of a category. It's a categorical concept. It should be preserved under equivalences of categories. And so therefore, if we could establish that indeed equivalences of categories preserve isomorphisms of the center of those categories, and we assumed that S was also a commutative ring, we can see that we would obtain the result via this chain of equivalences. So this is our overarching proof strategy for the next couple videos. However, so this is the motivation we have in mind, but a lot of these proofs really aren't much more difficult in a more abstract setting where we allow ourselves to be a bit more general. So what we're going to do is actually talk about things like additive categories, and talk about like the center of a general category and sort of build up theorems in a more general way like this. So with all of this motivation in mind, let's move towards the general definition of the center of a category. So because my writing is messy enough as it is, I'm going to avoid using too many fancy scripts. I like to try and write fancy C like this sometimes, but for now, I'm just going to write in ordinary C. So given a category C, the center is defined to be, so we write sort of this math frac Z. So we define it to be the collection of endomorphisms of the identity functor on the category. So in order to get a better look at this, it turns out, so maybe proposition I'll call this. Proposition. For any category, the center is a commutative monoid. Okay, what do I mean by that? I mean that it has a composition, so think like a group operation. There's some way to combine pairs of elements, which is commutative, and it has some sort of identity. So what is the commutative monoid structure? Well, it's the composition map is going to be given by composition of natural transformations, right? So if I have a morphism, so if I have an endomorphism of the identity functor, that is, I have a natural transformation, say eta, from the identity functor to the identity functor, and I have another natural transformation from the identity functor to the identity functor, then I can define their composition, eta composed with sigma. So I always forget whether one calls this horizontal or vertical composition, but it's one or the other. How is this defined? Well, it's enough. Remember, a natural transformation, I need some map on every object. So I simply need to define what this map does on the level of objects. And so I will simply define on each object, I will define this map to be the composition of the maps on the... Oh, I've written things the wrong way. My apologies. Well, some people like composition in that order. That is not the composition that I'm going to use. I just define it to be the composition. So how do we know it's a natural transformation of the identity functor? Well, I should take some morphism in my category, and I need to verify that this morphism, well, okay. First, let me say it this way. If I use the fact that eta is a natural transformation, I know that I get a commuting diagram of morphisms as such. Now, if I apply the fact that sigma is a natural transformation, I get a commuting diagram as such. But now this map, this large map here, is exactly the composition, right? And so we see by the commuting of this diagram, yes, in fact, this composition still defines a natural transformation. So it's closed under the operation. Why is it commutative? Let me pause to take a sip of water here. Well, I could say, for example, this morphism f that I began with. I could have taken that morphism to be eta x from x to x, and then using the fact that sigma x is a natural transformation of the identity functor, I conclude that I have a commuting diagram. But this exactly tells me that the composition is commutative. Now, the last thing I need to conclude that this is a monoid is I also need the identity. But of course, the identity function, so maybe I'll write 1x, the identity function from x to x certainly determines a natural transformation, right? Again, if I had some morphism from x to y, I apply the identity functor, nothing really changes. And so, of course, if I have the identity map in both of these components, then necessarily this diagram commutes. So the identity map on each object does determine an endomorphism of the identity functor. And under composition, of course, this serves as the identity. So this concludes the proof that, in fact, the center of a category is a commutative monoid. So now we would like to see, I mean, this really seems like a categorical concept. So we should verify that, in fact, it is preserved under equivalences of categories. So theorem. Let's say f from C to D and G from D to C be functors. And in fact, I'm gonna argue a slightly weaker statement before bumping it up to a full-blown equivalence. And suppose that we had a natural isomorphism from the composite of f and g into the identity on D. So a natural transformation, which is an isomorphism of functors. So then claim, I guess the beginning of the theorem statement is going to disappear here, but then the map capital phi determined by gamma, which goes from the center of the category C to the center of the category D, defined in the following way. Well, in fact, I'm going to begin some of the proof before I even finish making the statement. So let me jump down here, because in order to explain why this is a morphism, it's easier if I just basically begin proving it. So we already know from the statement of this theorem that we're trying to build a map from the center of one category to the center of another category. And because both of those things are commutative monoids, we want this to be a homomorphism of commutative monoids. So here's how it's going to go. Let eta be in the center of the category C. Now, somehow, I need to build a natural transformation of the identity functor in the category D. How can I possibly do that? Well, I'm going to need to come up with a morphism for every object in D to begin with, right? So given x in maybe D naught, we'll write for the morphisms, or sorry, for the objects in D. And in fact, I guess because we want a full-blown natural transformation, we should really start with, in fact, a morphism between two objects in D, right? So we have some morphism in D. And I've got this thing, eta, that lives in C. Somehow I need to get everything over to C to have eta interact with it. Well, from the hypothesis here, of course, I've got functors going between C and D. So first, I will apply my functor G. So we have Gx, Gf. That feeling when have GF, am I right? Am I right, everyone? So we have we applied this functor, we get a morphism in our new category, but now we're in the category C. And eta is a natural transformation of C. So therefore, I get a map, I get a commuting diagram, in fact. This is eta sub G x, eta sub G y. This will be I'm just applying to this morphism GF, I'm just applying the identity functor and the natural endomorphism of the identity functor. So now I have this commuting diagram. Great. So I got over to the category C. I got eta involved somehow in all of this. And now I need to get back over, right? The whole point was to construct a natural transformation of the identity functor in the category D. So to get back over to D, I'm going to apply, I can apply F, which will take me back to that category. So F, and of course, by functoriality, this will preserve the commutivity of this diagram. So now I've got this commuting diagram, which is all happening in D. And I'm going to have to play the cowboy game here a second to give myself more space. Yeehaw, yeehaw, yeehaw. And move this diagram down a little bit. Well, remember, from our hypotheses, we suppose that we had a natural morphism, that is some sort of invertible map, gamma, from Fg to the identity functor. So that means if we're considering, oh, didn't want to do that. If we're considering this morphism, f from x to y, then I apply both the composite functor fg and the identity functor. Gamma is going to give me a natural transformation, so some sort of commuting diagram from Fg. In the other component, though, I'm going to put here gamma x inverse, I should say, right? And now I have a commuting diagram there. This diagram is commuting, so I'm stacking a whole bunch of commuting diagrams on top of each other. And then finally, I'm going to, down here, I'm going to apply gamma x to get down to x. And I'm just using the exact same trick I used up above, except now this will be gamma y inverse. And now what do I have? If we forget the interior parts of this, I have this big commuting diagram, right? I'm just pasting 3 commuting diagrams together. So I now have this big commuting diagram with the morphism f on the top and the bottom. So really, what do I have here? This commutativity is exactly what's defining an endomorphism of the identity functor applied to the morphism f. So what I'm going to take for my morphism on the level of each object is simply this composition here. So now I can go back. Now that I've completed part of the proof, I'm going to go back and I'm going to finish saying what this is. So I'm going to take a morphism eta, and I'm going to send it where? I'm going to send it to, let me say that a morphism such that maybe for all objects x, it will be gamma x composed with f of eta of g of x composed with gamma x inverse. So I've already completed the proof that this is in fact a map between the collections of endomorphisms of the identity functor in either category. What we would still like to do is verify that this is a homomorphism of commutative monoids, and we would like to know, so furthermore, let me say, moreover, if epsilon is a natural isomorphism from GF to the identity functor of C, then phi epsilon is inverse to phi gamma. So that would finish the conclusion that we have, so a left-right inverse, I should say. And that would, so we already know by construction, once we do the direction for phi gamma, we already know basically just by changing variable names, because we chose all of these categories and names abstractly, that phi epsilon is going to be a homomorphism of commutative monoids. And so if they're inverses, that would conclude that we have an isomorphism of commutative monoids. Okay, so that's going to take us a little bit of work. So let's start with proving that this is a homomorphism of commutative monoids. So given, now I'm going to use alpha beta in the center of my category C. Let's simply just write this out. So we take phi, gamma, alpha, beta. So this is supposed to be some natural transformation in D. We can evaluate it at some object x. By definition, this is gamma x composed with f of alpha composed with beta evaluated at g of x composed with gamma x inverse. But this, so this is gamma x composed with, now the composition of two natural transformations on each object is just the composition of the individual natural transformations on that object. So, and then also, I'm going to do two steps at once here. I think you'll follow along. F is a functor, so it respects composition. So we get f alpha gx composed with f beta gx composed with gamma x inverse. Okay. And now let me just move my equal sign over a moment. What I can do is I can take, so this is gamma x, f, alpha gx, and I'm going to do, the mathematician's favorite trick, multiplying by 1, by multiplying by a fraction or something. I'll put gamma x inverse here, composed with, and here I'll put gamma x, so that will cancel out, just give me the identity. It really will be equal to the above, and you can guess what the rest is going to be here. F of beta sub gx, gamma x inverse, and sure enough, what do I have here? This is exactly phi gamma of alpha evaluated at x, composed with phi gamma beta evaluated at x. And so since we checked that the composition of these natural transformations is respected at every an arbitrary object, we can conclude that ultimately the composition of these natural transformations holds. So that gives us the composition law, but we are still missing, in order to be a homomorphism of monoids, unlike with groups, because with groups you get that it preserves the identity using inverses, but we don't necessarily have inverses in a monoid. And so therefore we should also check by hand that this preserves the identity. So we check gamma, let's see, gamma, phi gamma applied to the identity of, I don't want to do too many subscripts here because it's the identity of the identity functor. So let me just call it 1 for now. Of course, we can plug it into a test object. What is this going to be? It'll be gamma x composed with f of 1 sub gx composed with gamma x inverse. But of course, 1 sub gx, this is the identity morphism on gx. And because f is a functor, we know that it has to take the identity morphism to the identity morphism. And so this will be gamma x of the identity morphism of gfx composed with gamma x inverse. But now let us recall that gamma is a morphism, is an endomorphism of, or sorry, gamma is an isomorphism from fg to the identity functor. So in particular, if I take the identity morphism from, so 1x from x to x, I apply the identity functor and I apply fg to this. So here I'll have fgx. Here I'll have fgx. And of course, I'm applying a functor to the identity morphism. It has to take the identity to the identity. This will be 1 fgx. And then gamma is an isomorphism, of course. So here, I suppose I can write on this end, actually, which end should I put it on? Let's see. This will be, sorry, I should put gamma x inverse here. It doesn't really matter. The point is all the same. This diagram will commute. This is gamma x. This diagram will commute. So what does that say? I mean, that says exactly that this composition here really is just equal to the identity on x. And so therefore we have evaluated these two natural transformations at an arbitrary object, found that those morphisms agree, and so it must be the case that these are one and the same natural transformation. So that verifies the fact that that phi gamma is a homomorphism of commutative monoids. Fantastic. The last thing that we need to show is that if I had this extra isomorphism epsilon, let me go back up to the theorem statement. If I have this extra isomorphism between the other composition here, then that allows me, that will produce for me an inverse morphism between the centers of the categories. So we already know, by the work we've already done, we already know it will be a monoid morphism, but now we want to see that it will in fact define an inverse map, and that will allow us to conclude that the center of a category as a commutative monoid is preserved under equivalences of categories. So let's get into that. Okay, so by definition, so let's take phi epsilon, compose it with phi gamma, and apply it to some natural transformation eta. And we'll evaluate it at some x. And so now, by the definition, we'll outside in, by the definition of phi epsilon, this is going to be epsilon x composed with g of phi epsilon of eta at f of x. So I should be careful now. X is an object in the category C, right? Maybe I should clarify this point. So X is now, before we were using that to denote an object in the category D, I'm now using it to denote an object in the category C. And I want to check, we're trying to check that this is the, this composition is the identity. So we want to show what we're after is to check that at each object, my eta should be in here. At each object, if I evaluate this at x, the morphism I get is eta x. That's what we're trying to show here. Okay, so I just thought maybe I should clarify. Okay. So this is g of phi to the gamma of eta sub f of x composed with eta x inverse. I'm gonna need some more space, so gonna move my minus sign over here. Well, let's just recall that phi gamma eta sub f of x sorry, that should be on the outside here. So recall that this is going to be eta sub f of x composed with f of eta gfx composed with gamma fx inverse. Right? Okay. So now we know that eta is a morphism of the identity functor, right? So in particular, eta sub x, this is a map from x to x, and epsilon is a functor from natural transformation from gf to the identity functor on D. And so, the identity functor on C, my mistake. And so we can apply that. Again. We can take eta x, and we can apply both the identity functor to it and gf to it, and we'll get a commuting diagram. gfx, epsilon x, and down here, this will be gf of, my mistake. This will be eta sub gfx. Sorry, so I actually said things wrong. I'm not applying eta. Rather, I'm applying the identity functor to this morphism, and then because eta is a morphism of the identity functor, I get this commuting diagram. Sorry, I explained that backwards. Nonetheless, the point is that we get this commuting diagram. So what's the conclusion? Well, remember, we're assuming now that epsilon x is an isomorphism. So we can conclude that eta gfx is in fact epsilon x inverse composed with eta x composed with epsilon x. So how does that help us? Well, what I'm going to do is go back. Where are we here? I'm going to go back. Remember, in our description of what's going on here, we unpacked. This is what's going on in the middle of this whole thing, and now I realize that I can re-express this term. Where's my? I can re-express at least the eta sub gfx with these new terms. So here's what it's going to look like when I plug all of these things together. I hope you're following along at home, folks. What am I going to get? So this is phi, epsilon, phi gamma, eta, all plugged into x. Once I make all of those substitutions above, here's what I'm going to get. I better just write it below because it's going to take up a lot of space. We'll have epsilon x composed with g of, big braces here, gamma sub fx composed with f of epsilon x inverse composed with eta x composed with epsilon x, right? That's this result that we just used here. Then on the other side, I still have gamma sub fx inverse, and over here I will have epsilon inverse x. Okay. So quite complicated expression we have. And now, what am I going to do? I'm going to break this up even more. So I've got eta x of g. I'm still going to have my supergiant big braces, but now I'm going to use the functoriality of f to break up this expression. So bear with me here while I very carefully write everything out. So I'm using the fact, of course, in here that f is a functor, and so it preserves isomorphisms, and in particular, it's going to preserve inverses. So f of eta inverse, f of epsilon x inverse will be f of epsilon x inverse. What do we have? We still have a gamma sub fx inverse here. End of those big braces, and here we have epsilon x inverse. Okay, so we've really expanded things out. So now here's what we do. Let's switch colors again. So we're going to apply. So remember, this whole thing, this big expression we have, should just work out to eta sub x at the end of the day. That's what we're after. So what we're going to do is apply GF to the morphism eta sub x. And that's going to, so now after making this application, we have GF x over to GFX, and of course the morphism we have here is GF eta x. Of course we have our isomorphism of functors epsilon x, so that will give us this map down here, commuting with eta x. And now, so now I'm going to make, I'm going to apply f everywhere to this diagram. And the commutativity is preserved because f is a functor. And I'm going to need to play cowboy again, if you'll bear with me for a moment. So I have this big commuting diagram. Let me shift it down here for you. And now what are we going to use? Well, we're going to use the fact that gamma is an isomorphism from fg to the identity functor. So applying that here, I'm going to have gamma sub fx is going to take me from fgfx to fx, right? And same thing over here on this side. By the way, I mean, this diagram is commutative. And in particular, the map that goes here, right? So it's I'm applying the gamma to this copy of fg, right? So I'm left with the map f of eta x here, and this diagram commutes. Well, and just, I mean, perhaps this is already enough for you to see it, but it might just make it easier to see that we are going to have this big commuting diagram. So down here, oh, we already have the f of x down here. What am I doing? Silly. Right. So we've got, our focus is on this big diagram. Our focus is on this big diagram with all of the f of x's in the corners. That is to say, by the commutativity of this diagram, I claim that we have the following identity. I claim that we have that f of eta x composed with f of epsilon x composed with f of eta x composed with f of epsilon x inverse. I claim that this is the same as gamma sub fx composed with f of eta x composed with gamma sub fx inverse. right? That's just going around this diagram in different ways. So, I should say, and yeah, in the middle of this, right? Both of these are FGF. Both of these are FGF eta x. So, what I'm going to do now is go up to this big blue expression I had before, and I'm going to apply that new equality I obtained here. So unfolding that, what am I going to find? So let me rewrite everything down below. So I'm going to recall the thing I started with here. Plug that into f of x. What do I have? Hold on to your hats. What do I have? I have epsilon x composed with g of eta sub fx composed with f epsilon x inverse. Let's see. I already had that part written. So making the substitution, it should be gamma sub fx inverse composed with f of eta sub x composed with gamma sub fx composed with gamma sub fx inverse composed with eta x inverse. So you can see immediately that a bunch of terms in the middle are going to cancel. And what are we left with? We're left with eta sub x composed with g of f. So let me write g gf eta x composed with eta x inverse. And so finally, I claim that this will actually be eta x. Why is that? Because we have this commuting diagram. Let me see, gfx, gf eta x. Right? I'm taking the map again. I'm taking this map eta x, which goes from x to x. I'm applying gf to that. And I'm applying the identity functor to it, but epsilon is an isomorphism from gf to the identity functor. And so this diagram commutes. Of course, the epsilons are invertible. And so the conclusion is that this, in fact, is eta x, which is what we wanted to show all along. So at long last, this concludes the proof that an equivalence of categories induces, if you have an equivalence of categories, then you get, in fact, an isomorphism between the commutative monoids that are the center of the category. Okay, so I hope you're happy with that, and I hope this gives you some more power to prove some theorems. So prove some theorems. Tell me what theorems you prove with this in the comment section below. In the next video, we're going to talk about additive categories. We might actually compute the center of the category of rings and talk about more of the fun structure that we have there. So go prove some stuff.